গুড আফটারনুন সবাইকে। খুব ভালো লাগছে আমার, এবং আমার এটা অনেক দিনের ইচ্ছে যে আমি প্রফেসর কৃষ্ণেন্দু সেনগুপ্ত, সিনিয়র প্রফেসর ইন্ডিয়ান অ্যাসোসিয়েশন ফর কাল্টিভেশন অফ সায়েন্স, ওনাকে নিয়ে আসবো। তো এতদিন পরে সেই সৌভাগ্যটা হলো আমার, এবং আমার ছেলেমেয়েরা, আমার স্টুডেন্টরা, অন্য কলেজেরও স্টুডেন্টরা এসছে, আমার কলিগরা সবাই রয়েছেন। তো কৃষ্ণেন্দু দা আজকে যেটা নিয়ে বলবেন সেটা হচ্ছে যে অ্যাসপেক্টস অফ সিমেট্রি ব্রেকিং অ্যান্ড টোপোলজি ইন কন্ডেন্সড ম্যাটার ফিজিক্স, সাম রিসেন্ট ট্রেন্ডস। আমি কৃষ্ণেন্দুদাকে অনুরোধ করেছিলাম যে স্টুডেন্টরা যাতে বুঝতে পারে সেরকম লেভেলে বলতে। কৃষ্ণেন্দুদার সঙ্গে সানন্দে রাজি হয়েছেন যে আমি এমন কিছু বলবো না যেটা স্টুডেন্টরা বুঝতে পারবেন না। তো আমি একবার ছোট্ট করে কৃষ্ণেন্দুদা, একবার তুমি প্লিজ এখানটা এসো। জ্যোতির্ময় কলেজের তরফ থেকে একটু মিট করা হচ্ছে। কৃষ্ণেন্দু,
can you hear me at the back, or do I need the mic? It's okay, no? So then, okay. So I would first like to thank Partho and everybody else who has invited me here, and it's a real pleasure. So the thing is that first of all, I'm not going to make a claim that whatever I said here will be understandable to everybody. But I've tried to make it understandable, and one of the part of this process is that you guys ask me questions. Okay, so I don't have to finish anything, so I'm just going to show you a few transparencies. And if something seems to be not understandable or something which is not quite clear, just ask me. And we'll see where we can go from there. So, okay, so two things which we see on a day-to-day basis in condensed matter, which is in fact our bread and butter. One of them is age-old. It has come to light since 1950s, and that's symmetry. Okay, so one of the things that is really important in condensed matter is that a system breaks certain symmetries, and therefore its state gets quite interesting properties. And the way I'm going to demonstrate this is by telling you a little history of how superconductivity came in. And that will be at a history level, of course. That is one of the first systems that we realized which shows this principle of symmetry. And then something relatively new came up, which is the concept of topology, which cannot be sort of understood from this symmetry concept. So if I have time, I'm going to go there, but let's first talk about this symmetry. So here is a brief outline of the talk. So first is I'm going to talk about this introduction to superconductivity, and talk a bit about this symmetry breaking stuff. And another really interesting system that has come up, which can be understood just from an experiment level, let's say, not even going into detailed theories or anything like that, are these cold atom systems, which also host Bose-Einstein condensate, which is another example of this symmetry breaking in condensed matter. And if I have time, I'll talk a bit about graphene and show how this new material that has come up. But let me start with this superconductor. So, okay. So this was more than 100 years back. So in 1912, so this chemically known as this gentleman, what he could do is to liquefy helium. He was an experimental physicist, and his forte was to really look at low temperature. And he was one of the first persons in the world who could get a proper uninterrupted source of liquefied helium in his laboratory. And so he was trying to look at what happens to resistance of metals when you cool them to really, really low temperature. And this is roughly the plot that he showed, that he was taking mercury, okay, and trying to measure its resistance as he lowers the temperature. This was indeed done by a graduate student in his laboratory. And she pointed out that, I forgot her name, but she pointed out essentially that when one goes below this temperature, which is roughly 4.2 Kelvin, the resistance of the sample drops to a level which shows zero resistance. So what Kemal Gomez later noted is that mercury has passed into a new state, which on account of its extraordinary electrical properties may be called the superconductive state. So what he noted was that the experimental finding in his ledger was that resistance of the sample dropped below an experimental sensitivity when the temperature was taken below 4.2. So this is very important. You see that he being an experimentalist, you never say something like zero temperature or zero resistance or things like that. All you would say is that my apparatus is not sensitive enough to measure this resistance. And that's a very important lesson actually for anybody who is doing experiment. Because you can only say what you see. And that was his experimental stuff. So, so this was the first thing, and then people noticed that this is not only just a low conducting material, but it is something which is fundamentally different in the sense that it's not only the resistance that goes to zero, there are other properties too. And this took about 20 more years when this gentleman, Meissner, Meissner and his student Ostenfeld essentially found out something really interesting. So this was about 21 years from 1912. Okay? So what they found is that they were looking into this magnetic field lines. You know, this experiment that all of you do at some point. You put a magnetic material and try to map out field lines around that material. So he was doing the same thing but at a very low temperature, where he could essentially lower the temperature of the sample so that it goes into a superconducting state. And there, what he found is that once this temperature is so low that it goes into the superconducting state, the field lines along this around this sample gets pushed to the outer plane. It's almost as if the sample repulses this flux line. Okay? So these are the magnetic flux lines, and there's a cartoon picture, of course. And then you see that it's just there. So this effect led him to conclude that superconductors expel magnetic fluxes, and in other words, they are perfect diamagnets. So we see diamagnets, of course, among other things, like different materials and stuff like that. But here, the diamagnetic susceptibility, when you measure that, it's really, really large. So it's almost at this perfect diamagnet. Okay? So, of course, in reality, the flux is not perfectly expelled. What happens is that it penetrates a little distance and then inside the superconductor. And this, so there is this other gentleman called London who explained why this happens, and this is named in his name. It's called the London penetration rate. It's typically the distance that the flux penetrates inside the superconductor. So there is a, so this tells you that superconductor is. So this typically happens that it's not just a low resistance state. What this state is also, it has very interesting magnetic properties, which tells you that this is not just a, again, not just a good conductor, it's a very different state of matter. So the other thing that came up, which showed that why this is a good different state of matter, is apparent when you measure its electronic specificity. So those of you, when you take your first solid state courses, you will see that when you measure specificities of any substance, there are roughly two contributions to it. One of them comes from lattice vibrations, and that at low temperature typically goes as T cube. It's cube of the temperature. And then there is the electronic contribution, which goes as linear in temperature. So in metals, this thing, since there are a lot of available electrons, this linearity behavior is easily seen. However, it seems that when you cool the temperature and this metal goes into a superconducting state, this specific contribution goes to zero almost exponentially. Okay? And there is a sudden jump at the critical temperature at which the sample goes to a superconducting state. So this tells you that something fundamentally different is happening with the electrons inside the materials, and that is being reflected in the specific history. So these are all experiments in till 1950s which gave crucial clues to the fact that superconductors can be a really different state of matter. So people also looked into the behavior of superconductor in magnetic fields, and what they found is that there are two distinct types. So pure metals like lead or mercury, when you cool them, it so happens that if you put in a magnetic field, there is a critical field above which it goes to a normal state. So if you put too much of a field, the superconductor just gets destroyed. However, if for alloys like alloys of niobium, selenite or other things, what happens is that you start from a garden variety superconductor out here, but then you don't immediately go to a normal state. There is an intermediate phase where there is some region inside the sample which is metallic and some other region which is superconducting, so it's a mixture. And these are typically called type 2 superconductors. This field, BC, which is typical called a critical field for destroying the superconductor, here there are two of these, BC1 and BC2. And there are two typical fields which is required to take the sample out of the superconductor. Okay, so now a bit of phenomenology, what people tried to do before the microscopic theory came. The first thing is that people try to understand why, when you put in a magnetic field inside the superconductor, why is it so that the magnetic field gets excited? And this could be understood from a very simple classical point of view, simply from electromagnetism, Maxwell's equations. Okay? So there is one guess or answers that one has. It just says that the state of the electrons inside the superconductor is such that the momentum of this electron is just the applied vector potential. In other words, you know that this P is typically called the mechanical momentum, whereas when you apply magnetic field, there is something called a canonical momentum, which is pi, which is P plus Pa. So the postulate was that the ground state of the superconductor corresponds to a state of zero canonical momentum, and that tells you that P must be equal to this vector potential, from which you can get a current, because current is just the velocity, which is P over n times the density times the charge. Okay? So that's the charge current, right? NEV, the standard secondary stuff. And if you just put this expression of P, you find that the current is proportional to the vector potential that you have put. So the vector potential is because you have put in a magnetic field, and that's how you are looking at it. So you take this and you put this in the Maxwell's equation. Okay? Once you do that, you immediately see that because there is an A here and H can be written as curl of A, if you simplify this equation a little bit, you immediately see that the equation for H essentially is such that this is an exponentially decaying pattern. So this is a standard equation which can be solved by putting in H equal to exponential of minus x over lambda, and this lambda is the penetration depth. And from this simple analysis, not only could London explain that why the magnetic field decays inside the superconductor, he could also derive a typical length scale. Okay, that is the depth up to which the field is going to penetrate inside the superconductor. And this length is now known as London penetration. The first phenomenological theory which told one that how you could get a penetration depth out of, how you could get a length scale which tells you how deep the magnetic field gets inside the superconductor. Okay, so this is the phenomenon. So, but now at the end of the day, there is always this question: what is happening to these electrons? Why is the sample behaving like this? Now, to understand that, I'm not going to get into the details of mathematics of that, but just let's try to see, if there is a way to explain this phenomenon. Now, to that can be understood in the following sense. So, you see, when we look into electron conduction on a lattice, there is this background lattice which is almost static, and then the electrons move in the context of this background lattice. That model is typically known as the Jellium model. It just tells you that the background charge is like a static jelly, it's a background of static charge, and the electrons move in that background. However, of course, this is not entirely true because as we know in a metal there is this lattice and the ions are arranged in a specific pattern. So this, for example, is your typical potential well, but lots of them. That's one model which explains this lattice. The point is that the lattice, it turns out, is not static because these ions, they move around their mean positions. So it turns out that it is fundamentally important to explain superconductivity that these electrons sees this moving lattice, that is the vibration of the lattice, which are typically called phonons. Okay, so what people did was to come up with a cartoon picture like this. And imagine that a lattice can move, it can distort, this lattice positions can buckle a little bit. So if there is a negative charge, if an electron is present right here, what would happen is that these lattice points, which are positively charged, they are going to bend a little bit towards the electron because of the electrostatic interaction. It's an attraction, right? Because electrons are negatively charged and these guys are positively charged, and so they are going to attract a little. Now, what this means is that around this electron, there will be a higher density of positive charge. So if a second electron is passing by, it would see this higher density of charge and its trajectory is going to bend slightly towards this density. Okay? Because again of this electrostatic interaction, the attraction. So if I now take the lattice out of the picture, okay, then I would think that purely from the electron's point of view, the second electron gets an effective attractive interaction towards the first electron because its trajectory is bending towards the first electron. Right? So apparently this, okay, not exactly this, but a more sophisticated mathematical version of this was the first idea that two electrons, although they are both positively charged, there is a possibility that because of the presence of the lattice, they could have an attractive interaction between them. Okay. And it turned out that there's a key concept for superconductivity. However, this is not a theory because I have just told you something which is very basic. But I haven't taken into fact that there is this repulsion between the electrons, so there is no reason why this attractive force would be. I haven't also told you that that electrons are not really static objects inside a metal. Rather, they occupy fixed momentum states, which means they are all over the those are details, and people did take care of that. But this picture of having an effective attractive interaction between electrons due to the presence of this background lattice is really fundamental in understanding superconductivity. This is how one can have an effective attractive interaction between the electrons. And so what if you do have this attractive electron-electron interaction? So the answer to that first came from this Cooper, the so-called Cooper problem, where this guy, Leon Cooper, who was by the way a graduate student at that time with John Bardeen, and Bob Schiffer was a postdoc in that group. So they came up with this, and this solution was really Cooper's solution. So what they found is that they took this problem, but not in real space. They took it in momentum space, where two electrons are sitting on top of this Fermi surface. And they wanted to see that suppose these two electrons are there, and they have an attractive interaction because of the presence of the lattice, could there be a bound state between them? If so, then the electrons are just going to form that bound state to lower their energy and form a pair. Right? And it turns out that there is some complicated mathematics. I'm not going to get into that, but after you guys do that, it really turns out that these electrons do form a bound state. Okay? There's a few lines of algebra, and when you do your quantum mechanics in your third year or something like that, you're going to see that. But the point is that this was the first example of two otherwise negatively charged particles which are supposed to repel each other. They form an attractive, they form a bound state due to some effective attractive interaction. And it also turns out that the presence of this whole Fermi surface, that is this bunch of other electrons, out here, this whole block, which is this field Fermi circle, is very, very important for this process to happen. If this was not there, two free fermions or two free electrons, just in the absence of this, is never going to form this ground state. So this is what gave rise to the macroscopic theory. So what people said is that, well, if I put in two electrons there, then I see that they form an attractive, they have an attractive interaction, they form a pair. But these two electrons are nothing special. So every electron that you have near the Fermi surface starts forming this pair. And so initially this metallic Fermi surface, which had a lot of free electrons, now become completely unstable. Because all the electrons on the Fermi surface starts to form a pair with some other electron. And that new state where these pairs are formed, and these pairs, by the way, are called Cooper pairs in the name of Stephen Cooper. That new state with all these pairs of electrons, that's the superconducting state. And this is why. And from this, just from this consideration, it is possible to explain all these properties of specific heat and this magnetic flux expulsion and everything that we saw. And these calculations were done, it was beaten to death in 1950s and 60s, and people really understood what this state means. So this is sort of a brief microscopic explanation as to why superconducting happens. Let me just go with this. Actually, maybe I'll just first explain this. However, this ground state has another fascinating property, which let me try to explain this. So you see that suppose I have a magnet. So we all know that when my temperature is greater than the critical temperature of a magnet, I go into a paramagnetic state. And what does it mean? That if this magnet is a bunch of spins or orbital angular momentum or whatever, they can point a different, or spins can point along different direction, and it's a haphazard situation. When I lower the temperature, all the spins has to point along the same direction. And that's the new state, and that's called a ferromagnet. So all of you know what a ferromagnet is. But the interesting point is that, look, in a ferromagnet, it turns out that whether all spins point up or down or right or left, it really doesn't matter. All the spins have to point along some direction, but it's not the Hamiltonian of the system, which determines its energy, doesn't specify which direction it is to be pointing to. So the state of the ground state of the system just chooses randomly one. So this is an example of this famous statement by Anderson, who pointed out that just from this magnet example, that the ground state of a quantum system did not respect the full symmetry of its Hamiltonian. So the Hamiltonian, for example, of a magnet, if you look at it, it really doesn't care whether the spins points up or down or right or left, as long as they point in the same direction. But the state just chooses one of these many possibilities. And that's an example of symmetry breaking, because the state has chosen one of the many possible directions where the Hamiltonian doesn't care about. Similarly, in superconductor, you do have such a symmetry breaking. And this is, again, of fundamental importance for this. Another really interesting thing that happens with this superconductor is that when you keep on applying magnetic field, the field essentially penetrates in these circular patterns called vortices. So all of you have seen a vortex. We just take a bunch of water and just rotate it, but you see that the center forms a dip. That's an example of a vortex. This is somewhat similar, but this thing happens with electrons. And the center of this vortex is a region where this superconducting Cooper pair amplitude, probability of formation of pair, just goes to zero. Okay, but as you go away from that point, it again deconverges. So this is something that was measured in STM experiment. You take a scanning tunneling microscope and you try to look into this, and you can distinguish between metallic regions and non-metallic regions. And people saw in the superconductor that there are these different patches where this red means high density of electrons, which is the metallic regions where these pairs are destroyed and so you have free electrons. And this blue means that the pairs are there, you don't have free electrons. And so you see these patterns which are like this vortex patterns. So, let me so to conclude this part, what I wanted to say is that superconductivity is a phenomenon where the state of the metal, when it is cooled below a certain temperature, is fundamentally changed. The metal goes into a new state which breaks a particular symmetry. Okay? And I'm going to explain this a little more in context of DC. But this is the first example that people understood in 50s that how symmetry breaking occurs in quantum. And you see that all these different properties that you found in specific heat, in this behavior in the presence of magnetic field and everything, they are all consequence of this symmetry. So things fundamentally change. Okay, so any questions or anything? Otherwise, I will just move on. Come on, if anything is unclear, I can always try to explain.
I have a coordinate question. It may seem very silly, but our question is that when Cooper pairs form, is there any particular law of how the spins or how the quantum numbers will be related?
No, this depends on the material in question. So normally what happens is that the two electrons which are this which forms a pair, their spins would be up and down. So they are always going to be in a singlet state. But then there are special materials where things could be in a triplet state as well. So this really is a material dependent example. And so the singlet is typically called a S wave superconductor. And then there are this, the P wave, B wave, etc. So there could be, this is typically classified by their angular momentum channels. And those can be different, that depends on it. So, okay, so now I'm going to talk about a completely different system. And, okay, so this is about cold atoms. So, in the last, I would say, 25 years or so, people have really achieved wonders in these cooling techniques. So, people can now cool things to really, really low temperature. So, what does it mean by low temperature? So, in Calcutta, if things go here, everybody brings out their sweaters, jacket, monkey caps, everything. But that's human scale. So laboratory, there is this liquid nitrogen scale, which you have, which is the simplest low temperature scale that you have. And then of course liquid helium, which is about 4 Kelvin. However, and just contrast these numbers. So nowadays, people can cool things to about 10 to the power minus 9 to 10 to the power minus 10 Kelvin. Which is like a nano-Kelvin or even lesser than that. And that essentially makes this atom inside a laboratory the coldest known place in the universe. Because you know that outer space has something like 4 Kelvin, 2 Kelvin, 2.3 Kelvin, something like that as a temperature. So this is really where it goes, and I'm going to explain how people do this cooling. But there is one question that immediately comes to mind, that suppose you achieve such a temperature, how do you measure it? It's not like you can take your garden variety home thermometer and just stick it there, because it will immediately heat up the system and you are not going to measure anything. So there is a very interesting way that people measure this temperature, and that's another thing that I wanted to say. So you know that this is of course work by S.N. Bose, and pointed out that bosons, so these atoms are bosonic. So bosons, when you cool them, they go into this state which forms a Bose-Einstein condenser, right? So it turns out, and when you do your statistical mechanics, you're going to see this, if you look into this condensate and look into what state they occupy, they all occupy the zero momentum state, but not all of them, because because of temperature, some of them gets kicked out of this zero momentum state. So if you look at the momentum distribution of these bosons, you would see a huge peak around k equal to 0, which is the zero momentum state, and then there are some other. But how many atoms are kicked out of this zero momentum state and how many atoms get this finite momentum stuff, that really depends on the temperature of the system. And people know, the relation between that number and the temperature. So if you can measure the width of this peak, okay, you know how many atoms are outside this zero momentum state. And from there, you can get the temperature. And that's exactly how they measure the effective temperature of a Bose-Einstein condensate in a lab. So you create this Bose-Einstein condensate, and some way, which I'm going to explain in a second, you measure its momentum distribution of these bosons. You would get a peak structure. You look at the width of that peak. Knowing that width, there is a very straightforward formula which gives you the temperature. Okay? So people know how to do this. So these BEC which are formed and these cold temperatures which are achieved, they essentially are obtained by, the number, the temperature that you obtain is obtained by keeping in the width of the central peak in the momentum distribution of the process. So this is how we measure temperature. So these kind of systems, not only it requires new techniques for cooling and all that, it also requires new techniques for measurement, because this is not your standard garden variety laboratory stuff where you can measure things by ordinary techniques. So how do you cool these atoms? So here is another really interesting thing that one does. So typically these atoms are taken out of an oven where they form you take a collimated beam of these atoms from an oven and put them in a chamber and then apply conventional cooling techniques like liquid helium, etc., and you get them to a few Kelvin temperature, or maybe even a microkelvin, a millikelvin or so. But after that, the conventional cooling techniques do not take you any further. So you do this cooling by light. Okay? How do you do that? So you have a bunch of atoms sitting here, and you apply light from all directions. So what does it mean? These atoms see a bunch of photons coming at them. But as you know that every atom has a fixed absorption frequency. So these atoms have energy levels and it can absorb a photon if and only if you basically match the frequency of the photon to that line. Right? So what people do in the literature is typically called red detuning. What this means is that they keep the frequency of these photons, because this laser light frequency is something you can control in the laboratory, a little bit below the line, the width of the separation of the energy levels of that. And this they can do very efficiently. So why do they do that? That is because, you see, when the atom moves towards the photon, if you are sitting right on top of the atom, because of Doppler effect, you are going to see an increased frequency of that photon. Whereas if you are moving away, you are going to see a reduced frequency. So if you red detune the frequency to begin with, this means that the atoms are going to absorb these photons if and only if it's moving towards the photon. Because then their relative frequencies are very close to each other, right? This essentially means that whenever this kind of collision happens, the atoms dump their momentum to the photon, which means it's lowering its momentum, right? But lowering momentum for free atoms essentially means lowering their energy. And so this cools down these atoms, because after all, reducing temperature essentially is a mean of lowering energy. So there is a lot more details to this process which I am not going into. But the point is that this Doppler cooling of atoms, using Doppler effect and light to cool a bunch of atoms, is the first thing that came into picture for cooling this. And this was central for creating a Bose-Einstein condensate out of these atoms. This is what Bill Phillips and others did, perfecting this technique in the 90s. And that's why they could get the first Bose-Einstein condensate, I think around mid-90s in their laboratory. Okay. Now, after this, people do another thing, which is also very interesting. And this is really required to get into nanokelvin range temperature. This takes you up to a few microkelvins, but after that, everything saturates and you cannot really cool anymore. And then what people do is that they put these atoms, these microkelvin temperature atoms, into this magnetic trap. It's a trap like this. This energy, effectively, is also the energy axis. So atoms which are essentially at the top, they are higher energy, whereas the atoms at below are much lower. And then what they do is that they take this trap and slowly lower its top edge, so that the atoms which are at the top of the trap, they can simply escape. Which means that out of this collection, you are throwing out the energetic atoms out. Okay? So whatever is left has a mean energy which is much lower. And since mean energy essentially is temperature in any statistical mechanical sense, this also means that you have lowered the energy of this. This is, by the way, exactly the same mechanism by which your cup of tea gets cold in a winter morning, because it's evaporation. You see, you are taking these energetic atoms and you are putting them out. That's exactly what happens to these molecules inside a cup. They just move out because they can escape from the cup. And this process this is therefore called evaporating heat, because you are taking the higher energy stuff and getting them. And this happens to give you a temperature which is of the order of 10 nanokelvin, and now I think even in sub-nanokelvin range. And this is well below the critical temperature of any Bose-Einstein condensate that you would ever want. And this is how they make this Bose-Einstein condensate. So this whole cooling process, this starting from atoms in an oven to this 10 nanokelvin temperature, this is the work of Bill Phillips and I think this MIT person, I forget the name. Both of them, they essentially perfected this technique, which helped us to essentially look into this kind of stuff. So after this, people did something more interesting. What they did was to take this counter-propagating laser. So you have these atoms, sitting in a trap, and now you put this laser from both sides. In fact, from 6 sides if it's a 3-dimensional stuff. Now, the atoms, they always have a polarizability. Typical atoms, they can be polarized and they have a polarizability, and therefore they see an energy which is this polarizability times the intensity of the electric field that is. So alpha times mod E square, so standard electrostatics. And this alpha is tuned in such a way that it's positive. This means that because you have applied same frequency laser from either side, this forms a standing wave. Because you are putting right moving and left moving stuff, these two waves sort of hit each other and they form a standing wave pattern like this. But this means that the atoms, they are going to sit at the bottom of those laser potential, because that's why the electric field intensity is minimum. Right? Because if you have a standing wave, the electric field intensity goes as cosine in the spatial pattern, right? So the bottom of this cosine potential is the place where this intensity is minimum, and because it wants to sort of maximize this energy, what it does is to sit at the bottom of this. One traces mean that you can, if you make this deep enough, you can localize these atoms, because it's simply not going to move out of it. And this has some implication for this bosons, which I'm going to come. But before that, let me just put one more thing which is interesting. How do you measure, how do you know what happens to these bosons inside the trap? And this measurement procedure is also something which is very, very interesting. So of course the trap is very small. You cannot really take a picture or look into those traps directly. So the measurement procedure is something like this. So you take this trap, you pull the bosons, you do whatever you want. And then, suddenly, you switch off the trap and switch off all the lasers. So what would happen? The bosons which were in the trap now will suddenly feel that the trap is not there anymore. It's going to simply expand. But because it's a sudden expansion and it's a free flight, and now you put in a screen, let's say I put in a screen here, the bosons are going to come and hit the screen, just like this. It was here in the trap before, and then you have removed all the trap, it just moves, and if you put a screen here, it's just going to come and hit the screen sound. So you take that picture. Because the screen is large, you can basically take that picture. But now let's see how the boson hit the screen. The boson was sitting in the trap, okay, with some value of its momentum or velocity or whatever. Now suddenly the trap is not there and it's doing a free flight. What does that mean? The position of the boson after some time is just going to depend on its initial velocity. The free flight, right? X is equal to V. So if you can measure the distribution of the bosons in the screen, you immediately know the velocity distribution of the bosons inside the trap. So measurement of position distribution of these bosons on the screen gives you the momentum distribution or velocity distribution of the bosons inside the trap. Now let's see how that is do. So if your lattice potential is very, very small, that is V is equal to 0, this V naught is the lattice potential, then you are going to see this, that all the bosons just hit the center of the. Why is that? Because this means that most of the bosons have zero initial velocity, because it's in a zero momentum state, and that's a signature of a Bose-Einstein condensate. Because most of the bosons are in a zero momentum state. However, if you now keep on increasing this, okay, you see that this central peak will vanish, and out here, it's all smeared. Now, what does this smeared out pattern mean? That the bosons are everywhere on the screen, which means that their velocity inside the trap has all possible values. Right? So what this means is that it's completely delocalized in momentum space, and by the uncertainty principle, that means it's very well localized in real space inside the trap. So this is a signature of localization, whereas this is a signature of spreading. A Bose-Einstein condensate which is at zero momentum state. So when a particle is in a zero momentum state, it's almost like a wave, it's everywhere. So that's it. And in between you see a transition from one state to the other. But this state, this BEC, is yet another example where the system essentially goes into a symmetry broken state. Because Bose-Einstein condensate typically breaks a symmetry. The phase of the particle becomes uniform for all particles, and that is the signature of this. So here is a cute picture of what happens when you measure this kind of things. This is what you see when you measure things in a Bose-Einstein condensate phase, and this is what you see when you measure things when the lattice is given. So this is localization of bosons. This is delocalization. Okay, again I'm for this. How much time? No, actually, can I? So it's 4. Okay, so I'll just. So again, I'm not going to get into the details of the theory, but let me just come to. So what I wanted to say here was that this really systems of atoms and light are something which is allowing us to look into some very fundamental properties of bosons. Something that Schopfling was predicted almost 100 years back. And this is, by the way, in the 90s, this was the first time when this was man-made Bose-Einstein condensate came in the picture. People had helium before, and there was a long time debate, mostly between the Russian schools and rest of the world, whether helium was really a Bose-Einstein condensate state. So that was a murky debate, but the point is that after this, people really got convinced that Bose-Einstein condensation is a definite state of matter. And so it's good news.
আমি একটা ছোট্ট আমার একটা ইয়ে রাখবো, সেটা হচ্ছে যে যখন তুমি ডপলার কণিকা দেখালে, হ্যাঁ, তো ওইখানে যেটা দেখলাম সেটা হচ্ছে আমি ওই সিগমা গুলোর সিগনিফিকেন্সটা বুঝলাম না, মানে ওটা কি ফ্রিকোয়েন্সি একটু বেশি আর তারপর একটু কম, মানে ডপলার
so point is these sigmas are the polarization of the so it turns out so this polarization, their relative orientation, etc., everything plays an important role in how much you can cool this thing. It's not central to the cooling process per se, but when it comes to how much you can cool it, the limit to which you can go.
So do we need the atoms to move relative to the
no, the atoms are there in the track. They have their own motion. But the photons, when they move towards an atom at any given point, then there is preferred absorption. That's the only thing that is.
In the absorption period, so let me
okay, fine. So let me ask. Let's keep that, but let me try to answer that. So what happens is that so when you essentially do this scattering, when the scattering happens, the atom deposits its momentum in the photon. In the process, it absorbs the photon, and therefore it goes to a higher energy state. However, after some time, there is a spontaneous emission. But this emission being spontaneous doesn't depend on direction. So, if the emission is in the same direction as the photon, then of course the atom doesn't do anything, it's in the same energy state. But if it is in the other direction, then it lowers its momentum. Because it absorbs, it deposited momentum in one direction, and it again emitted the photon in such a way that it gets a kick in the other direction, opposite to its direction. So, because this is a statistical process, on the average, this absorption and emission process always lead to lowering of so that's okay. So I didn't want to explain this in detail because it's a bit complicated, but okay. So okay, and here is the last thing that I wanted to talk about. This is called graphene. So this is a two-dimensional material of carbon which came up, and this came up in 2005, even after Bose-Einstein partnership. And this is one of the first things that told us that we could have the role of topology in condensed matter. So I'm not going to get into the details of topology and stuff like that, but let's just look up a little bit about graphene. So all of you know graphite. Graphite essentially is something which is there in your pencil. Okay, so that's the standard material, specific allotrope of carbon. So graphite is this 3D allotrope, and this is the structure of graphite. So you have these hexagonal planes which are tied to each other. The bonds are very strong in plane, and they are quite weak out of plane, which means that graphite has very anisotropic property. So it's a good conductor of heat and electricity along the plane, but it's a very bad conductor of heat and electricity outside across this path axis. And by the way, one of the first few experiments on this anisotropic properties of graphite was done by Krishnendu in India. This was in the 1940s. And those were really seminal work which established this anisotropic properties of graphite. So the point is that what is graphene? Graphene essentially turns out is one of these hexagonal planes of graphite. So if you could have separated out just this one of these layers, okay, not all of them, then you get something which is called graphene. So experimental separation, people have been trying this for some time, but experimental separation of graphene has been a long-standing challenge. And the reason is the following. That typically what people do to get these few layers of graphite is cleaving. So you take a graphite crystal and you start chopping up stuff. And you do this very finely. But the point is, no matter how finely you do this, you get to a few hundred layers, but not lesser. It's impossible. So apparently when Andre Guy, who first did this, was doing this, he gave this problem to one of his graduate students who tried this for quite some time. And it turns out that 3 months into this, he got completely frustrated. Trying to chop off pieces of graphite day in, day out in a laboratory. And we came to Gaim and saying that, look, this cannot be done. So Gaim, of course, being the busy advisor, was busy with something. And he said that, why don't you go and try some more? The student replied, why don't you go and try it? Okay, so, and then Gaim started thinking about it, which was a very interesting thing. And he suddenly realized that the student was absolutely correct. You cannot really get a few layers of graphite. But he came up with a very interesting solution. Every time when you do this cleaving, just before you do the cleaving, you polish the surface of graphite with some scotch tape. You take a piece of scotch tape and you polish the surface so that it's really shiny, and then you cleave. He realized that while polishing this surface of graphite with the scotch tape, there are these flakes of little flakes of carbon which gets absorbed in the scotch tape. And typically people throw them off. That's a standard practice. However, he, on one fine morning, he just took one of those things and tried to look into this under microscope. And he found that he actually have a few layers of graphite, or rather graphene, some of them are even single layers, attached to that scotch. What the cleaving couldn't do, the polishing did this very well. And the reason was that this particular, this bond between the different layers are weak enough so that polishing the surface like this could bring out one or two layers. So after that, all he did was to take this piece, which was the first known graphene. He put some electrodes around it so that they can make some measurements about this thing. And this was the first science paper, which showed that indeed this two-dimensional structure of graphene could be realized. And apparently, there was this also solved a long-standing debate in the sense that it was told that freestanding two-dimensional structure really cannot exist. Because if you try to do that, it's simply going to roll under its own weight and form a curly structure. But this didn't happen, and one of the reasons it didn't happen was the scotch tape, which provided the surface on which you could lay this thing. So this was really revolutionary when it comes to material. The first known two-dimensional material that one. So a little bit about chemistry of graphene. So you see, so if you remember your higher secondary chemistry, essentially carbon is all about sp2 orbitals. Right? So you have 6 of these, and when you bring these 2 carbon atoms together, what happens is that these, some of this orbital forms what is called a sigma bond, because these sp2 is hybridized, and the pz orbitals of carbon, which was left alone, those forms the pi bond. And when you bring a lot of them together, these pi bonds essentially forms a band, which contributes to the electrons. So the whole physics of graphene, when it comes from material perspective, comes from this pi bond, and this band, which is formed by coalescing these different pi bonds, is called the pi band of graphene. So, but for us, theoretical physicists who just study models, the problem of graphene is this hexagonal lattice, this honeycomb, as one says. So it really looks like a beehive. That's why it's called a honeycomb lattice. And this honeycomb lattice essentially has electrons which hops from one side to another. So it has these electrons which hops from one side to another, and that's what brings graphene its structure. So without going into details of this, because I don't really want to bore you with mathematics, let me just point out one small thing. So this is something important for metals. It's called Fermi surface, which is the standard thing. So how do you arrange electrons in a metal? So what do? So it's like a particle in a box kind of thing. You can think of this metal as a box, and there are these different momentum states. So you start filling electronic states according to Pauli principle. You cannot put 2 electrons on the same state. Of course, if they are up and down spins, you can put them in the same state, but not otherwise. And so you fill out this, these different momentum states, starting from the lowest state, and you go higher in energy. because you want to find out the lowest energy configuration, which is the ground state of the system. Now check for the lowest energy configuration. However, you only have a finite number of electrons. It's a Avogadro's number, but it's still a finite number, right? N electrons, let's say. And when you finish, there are these momentum states which are occupied, and then there are these other momentum states which are empty. So this occupied region gives you a field region of 3D momentum space, because for example, if you have a p square over twice m and you fill the first 10 states, you're simply going to get a sphere. It's the equation of a circle. So that's the equation of a circle. So the surface of this field sphere is, or the surface of this field region is typically called the Fermi surface. And it turns out that if you have a 3-dimensional object, this surface is a 2-dimensional stuff. If you have a 2-dimensional object, it's a 1D stuff, and so on. It's 1 dimension less than your total dimension. Because just think of p square over twice m. You get a sphere of field region. The surface of that is a 2-dimensional surface, right? It's a surface of a sphere. But however, in condensed matter, because of anisotropy or dispersion, because the electrons hopping along x and y and z could be all different, you get several variety of shapes and sizes of these Fermi surface. So this is the Fermi surface of a class of compounds called cuprates, which are your high temperature superconductor. This roughly looks like a square. This is for another class of compound which is detuning, which looks like a cylinder. This is for some organic conductors, which looks like some bent lines. So it can be in all shapes and sizes. But mostly what happens is that if you have a d-dimensional solid, which is d equal to 3 is this example that I gave, then it's a d-dimensional d-minus 1 dimensional surface. So a Fermi sphere, the surface of it is 2-dimensional. In graphene, it so turns out, if you do this calculation and you try to find out its energy band and see, it turns out that something very interesting happens. Graphene is a 2-dimensional material, and you therefore expect a Fermi line, right? A line of points up to which the thing is filled, but it turns out that there are these distinct points that come out for reasons I'm not going to explain because this is a bit complicated. And if you focus, so this is the valence band of graphene, which is all filled. This is the conduction band. And you see that the valence and the conduction band come and touch at discrete points. And these points are the Fermi points of graphene. If you expand around this, you get systems with linear dispersion, which mimics something called Dirac electrons, which we are going to look at when you do relativistic quantum mechanics. But this is very special. Normally this doesn't happen. Okay. And here, therefore, you get something analogous to Dirac physics, which is not generally seen in condensed matter, and that's why graphene is special. And this Dirac physics is always associated with some topological properties, and that's why graphene is the first material which showed this topology. But I'm not going to get into the details of this, but the only thing I wanted to mention is that this 2-dimensional material, instead of having a Fermi line, has this discrete point around which there is band crossing like this. So the energy dispersion is linear, and that gives you a Dirac. So when you read your relativistic quantum mechanics, maybe in third year or maybe after that, you're going to appreciate why this linear dispersion is called a Dirac cone. I'm not going to get into that right now. But the point is, what I'm going to trying to impress on you is that really material physics can give rise to this kind of structures, which touches aspects of basic physics. So I think I'm going to stop here, and some questions would be helpful. Yes. না দুটো আলাদা সুপারকন্ডাক্টরটা এমনি মেটেরিয়াল আছে বোসন সিল কন্ডেন্সার এর অ্যাটম আনলাইক আছে মানে দুটো কমপ্লিটলি আলাদা সিস্টেম আমরা যখন ইকুইলিব্রিয়াম টেম্পারেচারে যাচ্ছি এটা বিসি আছে আমরা যেটা লোকালাইজ ডিস্ট্রিবিউশন দেখলাম তো এখানে ইউজুয়ালি একটা সিম্পল স্কোয়ার ল্যাটিস বা কিউবিক ল্যাটিস নিয়ে লোকে করে, কিন্তু অন্যান্য ল্যাটিসও তৈরি করা সম্ভব, কিন্তু তার জন্য লেজারগুলোকে অন্য অনেকভাবে ওরিয়েন্ট করা, সেটা কমপ্লিকেটেড, কিন্তু সিম্পলেস্টই হচ্ছে একটা কিউবিক ল্যাটিস। খুব একটা করাই না, খুব একটা করে না, ল্যাটিসটা হলেই চলবে, ল্যাটিসের জিওমেট্রিটা খুব একটা বেশি ম্যাটার করে না।
Any more questions?
হ্যাঁ,
I have actually two questions. That is one, that in case of superconductors, you mentioned about the vortex formation. That can be seen from the translation electron microscope, TEM or STM.
yes.
So I want to know that is this property that showed you, is this only the case where superconductor explains this vortex kind of thing? We can generate this for other materials.
You can generate this for BECs as well. So anything which has this symmetry broken state, you have an analog of this vortices. Okay. So in magnet there are substances called fermions, which you can look up. Those are analog of vortices there. So whenever you have this symmetry broken states, a particular type of symmetry broken state, superconductors or BEC, you are going to see this.
And another question is from this graphene. Graphene is actually that electron of carbon that particularly shows that energy and K are basically linear in relationship.
Yeah.
In this case, so that is the special thing of graphene. I want to just know that from that dispersion relation, can graphene show some flat bands kind of thing? Or
No, graphene doesn't show flat bands. It's usually always linear. Flat band physics typically requires.
X or Y.
No, flat band physics typically requires strong interaction. Graphene is interacting material already, but it's not that strongly interacting that it is flat band. It usually does.
Any more questions?
Yeah.
Four.
Sir, actually, from this point, on this image of graphene, so actually there are two bands exist, plus minus EK from that. Actually, this written.
This and that, right?
That is that. So from this you can conclude that graphene has actually more band there.
No. This is important. You see, this is a picture in momentum space. ঠিক আছে? হ্যাঁ, এবার তুমি যদি এখানে থাকো, তাহলে দেখো ভ্যালেন্স আর কন্ডাকশন ব্যান্ডের মধ্যে অনেকটা গ্যাপ আছে, কিন্তু শুধুমাত্র এই স্পেশাল পয়েন্টগুলোকে ভ্যালেন্স আর কন্ডাকশন ব্যান্ড টাচ করছে। তো তোমার যদি এবার একটা হাফ ফিল গ্রাফিন থাকে যেখানে ভ্যালেন্স ব্যান্ডটা কমপ্লিটলি ভর্তি আর কন্ডাকশন ব্যান্ডটা খালি, তাহলে এই পয়েন্টগুলোতে তোমার কোনো ব্যান্ড গ্যাপ নেই, কিন্তু অন্য সমস্ত মোমেন্টামে তোমার একটা বিশাল ব্যান্ড গ্যাপ আছে। তার মানেটা হচ্ছে যে যখন তুমি লো এনার্জি ফিজিক্স দেখবে, মানে তুমি একটা ছোট এনার্জি স্কেলের ফোটন দিয়ে কিছু একটা এক্সাইট করার চেষ্টা করছো, তখন তুমি শুধু এই পয়েন্টগুলো থেকে রেসপন্সটা পাবে এফেক্টিভলি। সেই জন্য এইটা হচ্ছে ইম্পর্টেন্ট।
আর কারো কোনো কোয়েশ্চেন আছে? হ্যাঁ।
আচ্ছা, আমার যে প্রশ্নটা আছে এরকম যে আপনি যখন হালকা করে লেখাগুলো বলছেন কুলিং অবস্থা, তখন বললেন যে টেম্পারেচার ধরে করতে যেটা করতে হবে যে একটা ডিসি ফর্ম করে তারপর ডিসি সেন্ট্রাল মোমেন্টাম ঠিক করতে। এটা তো হচ্ছে একটা বোসনিক সিস্টেমের জন্য হতে হবে। যদি ধরো একটা ফার্মিয়নিক একটা কালেকশন অফ ফার্মিয়নকে আমরা ফুল করতেছি, তখন কি করে জিনিসটা?
হ্যাঁ, তখন ব্যাপারটা এত সোজা না। ফার্মিয়নের দুটো ঝামেলা আছে। একটা হচ্ছে ফার্মিয়ন সিস্টেমে ফুল করতে গেলে সেটা হচ্ছে প্রথম ব্যাপারটা যেটা হচ্ছে যে ফার্মিয়ন সিস্টেম অত সহজেই ফুল করা যায়। তার কারণ হলো ওখানে পাউলি প্রিন্সিপাল থাকে, ফলত তুমি সবগুলোকে কাছাকাছি নিয়ে আসবে, মানে there is a huge obstruction to that. হ্যাঁ, সো এনার্জি ডিস্ট্রিবিউশনটা অনেক। আর একটা যেটা লোকে করে সাধারণত, যে তোমার যদি ফার্মিয়নের ডেন্সিটিটা জানা থাকে তাহলে তুমি ফার্মি সারফেসের যে রেডিয়াসটা সেটা তুমি জানতে পারো। তো এবার ওরা করে কি, ক্লাউডের ডেন্সিটিটা মানে রেডিয়াসটা মেজার করে। যদি ওটা 0 টেম্পারেচারে হয় তাহলে ওই রেডিয়াসটা রাফলি ফার্মি সারফেসের রেডিয়াসের সাথে মিলে যাবে, কিন্তু কতটা বড় হচ্ছে সেই অনুযায়ী কতটা টেম্পারেচার, কারণ তাহলে অনেক বেশি এক্সাইটেড স্টেট থাকবে, সেখান থেকে একটা ইয়ে করে। বোসনটা তো একটা পয়েন্টের অ্যারাউন্ড যে জিনিসটা মেজার করে, এখানে পয়েন্ট নয়, সেটা সার্ফেস না। তো সেগুলো কমপ্লিকেটেড ক্যালকুলেশন, কিন্তু লোকে সেগুলো করেছে।
any more questions? In that case, I would like to thank the speaker. Thank you, Krishnendu for coming. আমার কাছে এটা একটা খুব মানে enthralling lecture কারণ this is the first Condensed Matter Physics lecture that I have been attending. মানে আমি কখনো কোনো Condensed Matter lecture শুনিনি। আমার এতটাই মানে I was completely engrossed into the slides. এত ভালোভাবে বললেন এবং এই জিনিসগুলো সত্যি কথা যা ফিজিক্স আমরা পড়েছি বা যা পড়ছি সেটার সঙ্গে রিলেট করতে পারা যাচ্ছে। এটাই সবচেয়ে খুব ইম্পর্টেন্ট জিনিস। আমি জ্যোতির্ময়ীকে আরেকবার ডেকে নেবো।